south of the US, so you'll hear a bit of a muddled accent occasionally. I'm here to tell you all about not just gravity and gravitational waves, but a new type of gravitational wave that we've recently discovered. This is a gravitational wave that's ultra low frequency, and it's a background of gravitational waves coming from all over the universe. First of all, though, we need to understand what gravity actually is. I think we're used to thinking of gravity as Newton saw it. Here's a picture of something that almost certainly didn't happen. An apple falling on Newton's head or in front of Newton, giving Newton the inspiration for how gravity worked and how it's a universal law. Of course, Newton came up with this and many other physical principles while under quarantine from a plague outbreak, having been sent down from Cambridge. And of course, we had some of that recently. Newton had a lot more time to think more introspectively, though. We'd be a lot more distracted, I think, by modern technology and other things. But the story here is that 1687, Isaac Newton published his theory of gravity, which says that more massive or objects that are closer to each other will feel a stronger attractive force. This was an incredibly successful theory. It explained all aspects of gravity in the universe, how the moon is orbiting the Earth, how the Earth is orbiting the sun, and it extends outwards to other parts of the universe as well. It was so successful that it worked for over 200 years and was successful enough to get us here, and is successful in navigating probes throughout the solar system. Now, even though it's a very, very successful theory and is one of the most beautiful theories of all time, it had some problems. And those problems started to exhibit at the latter half of the Victorian era, essentially, in the late 1800s. And those theories led to some problems, which was it couldn't explain Mercury's orbit. So Mercury had a problem with its orbit. It seemed like Mercury's point of closest approach to the sun was actually advancing. It was moving, precessing, we would call it, around the sun. And Newtonian gravity could not explain this. It had a fundamental problem. And because there'd been similar problems like this in the outer edges of the solar system, particularly involving perturbations to Uranus's orbit, people started thinking about exoplanets because this is how Neptune was discovered. You look for problems and you posit that maybe there's another planet actually somewhere out there in the depths of space. So people actually started looking for planets that were closer towards the sun than Mercury. And this secret exoplanet closer than Mercury was even given a name. It was called Vulcan. And this was 100 years before Star Trek. People started looking for this exoplanet, and there were lots of hoax, calls to various observatories around the world, people saying that they'd found it, amateur astronomers seeing some speck and thinking, that's a secret exoplanet. It turned out to be false. There was no exoplanet. What in fact was needed here was a complete overhaul of the theory of gravity. It's not that Newtonian theory is wrong, it's just that it's replaced by a larger theory that has Newtonian gravity as a part of it. And this extra theory was given to us by this guy. This is Albert Einstein, of course, one of the most famous images, I think, of a scientist ever. And his theory was that gravity is really just a byproduct. It's a thing you get free by describing the universe as being made of flexible space and time. The idea that you can actually warp space and time. And things that we call orbits, planets orbiting around the sun, the moon orbiting around the Earth, or even the motions of galaxies, all of that is really just objects that are trying to go in as straight a line as possible, but they're traveling in space that's intrinsically curved. And so a path that is straight as possible through curved space is actually a circular orbit, where it gets deflected. So you can see that in this image here. This is a bowling ball in the middle of a trampoline, and an object that's lighter than that, like a golf ball, is trying to orbit around it. It's trying to move in a straight line, but it's moving in this curved gravity well. And so really, this changes our theory of gravity from just a thing that pulls other things to something that is saying something even more deep about the nature and the fabric of space-time. Now, because you can actually warp and create dents in space-time, and really orbits are all just paths that are trying to go as straight as possible in curved space-time, you can actually make ripples in this space-time as well, in this fabric. So in the same way that you can put a bowling ball in the middle of a trampoline and it'll sit there and create a dent, and that's gravity, you can also move that bowling ball up and down and it'll create ripples in that fabric, okay? And so we can make ripples in the fabric of the universe. These are called gravitational waves. So Einstein's larger theory of gravity allows space-time, this combination of space and time together in some four-dimensional larger union. It allows it to stretch and squeeze to make waves. These waves will travel outwards at the speed of light. The problem is that space-time is incredibly rigid. And so in order to make waves that are loud enough for us to actually measure, you need to have the most extremely gravitating objects in the entire universe to warp space-time, effectively churn up space-time to a large enough level that we could actually measure them. And so what we're looking for are things like colliding black holes or other ultra-dense objects like neutron stars or white dwarfs. But black holes are the classic source. And so I'm sure everyone here knows or has heard of black holes. Basically the most extreme areas of gravity in the entire universe. You can think of it like a puncture in the fabric of space-time. It's pure gravity. There's no star there. There's no matter. It's just an area of extreme gravity where, as far as we know it at the center, all the laws of physics break down as we know them. So it's the most extreme environment possible, but a great source for gravitational waves. So what I'm showing you here is a simulation, a computer simulation of two black holes, and I'm going to start it in a second. They're going to move around each other in an orbit. And as they're doing that, you'll notice that the light from the background stars is going to be bent and lensed in interesting ways. And so as the black holes are orbiting each other, they're acting as a source of gravitational waves. So they're going to send out gravitational waves. Those gravitational waves will leak energy out of this pair of black holes, and they'll get closer together. So essentially, the orbit of this pair of black holes will start to decay. And as it decays and the black holes get closer together, it will emit gravitational waves even more strongly until eventually this entire process just results in the black holes colliding together. Now, it's not going to be a very interesting or extreme thing when they do collide together because there's no matter present. It'll just look like two water droplets merging to form a larger water droplet. Okay, so these black holes orbit each other. They start out at a certain distance, but then they'll get closer and closer together. And you can't see the gravitational waves being emitted because we can't see the waves of gravity. It's not something we can see with the naked eye. But eventually you form this larger black hole. Now, the ways we have to measure those kinds of gravitational waves are now very successful. So over the last almost 9 years, gravitational wave scientists have been measuring gravitational waves from black holes and sometimes neutron stars using something called LIGO. LIGO is the Laser Interferometer Gravitational Wave Observatory. There's one in Washington State in the US. There's one in Louisiana in the US. And there's another type of detector also in Italy. There's one in Japan, and there's one being built in India as well. So there's now this global network of these interesting, really L-shaped instruments. So this is 4 kilometers long on each length of the L. What this is doing is sending beams of lasers along each of these L shapes, along each of these arms. And as the beams come back again, you look for an interference pattern of the laser light. And if there's no gravitational waves present, there's no interference pattern. The beams are initially sent out pretty much in sync with each other. But when they come back, if there's been gravitational waves that have come through the system, come through this detector, what happens is it will stretch and squeeze those detectors. It will stretch the actual length of those L's in one direction, and it'll squeeze the other L. So the laser light that initially starts out in sync will come back and form an interference pattern. And this is what the gravitational wave would look like when it was coming into this system. We couldn't see this. This is just a visualization. But it's going to stretch one of these arms, and it'll compress the other one. This is very, very small. This is incredibly small, and yet we've been able to measure this. So it's extraordinarily successful as a detector. Now, this is what happened on September 14th, 2015, before I think some people in the audience were born. But this is now history, because what you're seeing here is something that is 10 to the power minus 21. Now what that means is we've had to pick up length changes in those arms, 4 kilometer long arms, that are corresponding to a sort of fractional length change of 1 in 10 to the 21. That's equivalent to trying to measure the distance between Earth and Alpha Centauri, the next star system over, a few light years away, to the accuracy of the width of a human hair. Okay? But it was done. And what you're seeing here is the slow kind of spiraling pattern of these black holes orbiting each other and then getting closer together. So the waves, it kind of looks noisy here because it's a detector, there's some noise in there. But it gets closer and closer together. The spikes get larger and larger and closer together because the frequency is increasing. The black holes merge and you get this big burst. And then it settles down again. We call this phase the ring down because actually mathematically we can also almost treat it like a bell that's been struck because it vibrates at harmonics and then it settles down again. So this became history. Einstein was proven right yet again. It was almost 100 years since he actually posited the existence of gravitational waves. And Einstein's history of gravitational wave belief is kind of checkered because he came up with the idea of gravitational waves. Then he wrote a paper in the 1930s saying that they didn't exist. And then he was finally convinced that they did exist again. And it wasn't until the late 1950s that people actually believed that gravitational waves were real and not just some mathematical magic. But this is great. This has pushed us into the era where we can measure black holes colliding using something that's not light. This is pure gravity being detected. And because it's pure gravity, we don't need other objects around. We don't need matter. We don't need light from stars. We can just measure a completely different side of the universe, sometimes called the warped side of the universe, which gives us access to things that don't send out light, like black holes. So that's very great. We've been able to measure gravitational waves from black holes that are about the mass of the sun or slightly bigger than the mass of the sun. Why look elsewhere? Why try to do it a different way? Well, it's because this is how astronomy started out, really. And even earlier than that, we were just using the naked eye. But as we've been able to measure other parts of the spectrum of electromagnetic waves, we've opened our eyes to greater phenomena in the universe. This is the entire spectrum of light, gamma rays up to radio waves. And if we'd only restricted ourselves to this region, this small sliver that we can actually see, we wouldn't have seen any of this stuff over here. So as we've opened our eyes with new types of detectors across the electromagnetic spectrum, our knowledge of the universe has increased. And the same is true of gravitational waves. In some ways they're like light. They travel at the speed of light. They have wavelengths and frequencies. It's just that we can't use regular telescopes to observe them. But they do have wavelengths and periods. So this is the spectrum of gravitational waves. At the top here are the periods of the waves, so basically the time taken to get from peak to peak of the waves. And this is the frequency, so the number of cycles per second. And up here, towards the right-hand side of the screen, are the types of gravitational waves that were found in 2015 and later. So these are ones where the periods are seconds or milliseconds. The frequencies are about 10 hertz to a kilohertz. And up here you've got binary mergers. That just means pairs of stars that are merging together. And the masses of these stars are roughly the mass of the sun, up to maybe 100 times the mass of the sun. But if you want to find even more massive black holes, really the monster black holes that sit at the centers of galaxies, you have to go much, much lower in frequency. And that's where my type of detector comes in. So I'm interested in finding the most gargantuan black holes in the entire universe. These are billions of times as big as the sun, sometimes even tens of billion times as big as the sun. And so we have to use a radically different type of detector. This is not something we can do on the Earth. It's not something we can do in the solar system. We have to use the galaxy itself as one gigantic antenna for these types of gravitational waves. So first of all, why do we think these types of monster black holes even exist? It's because we've now actually directly seen them. You might have seen this famous image. It comes from a collaboration called the Event Horizon Telescope that directly imaged Sagittarius A star which is a 4 million solar mass black hole in the center of our galaxy. And that's pretty small. This is a very dinky black hole compared to the other big black holes that are out there, because our black hole is very small, our Milky Way galaxy is very small compared to other galaxies. So if we want to measure even more massive black holes, we need a different type of detector, and we know that these types of black holes exist. So if you have pairs of galaxies that are out there in the universe and they collide together, and this happens often in the history of the universe, it's not going to happen to us for another few billion years, but it happens elsewhere in the universe. And each of those galaxies has a gigantic black hole at the center. So really it's like a seed at the center of a piece of fruit. There's a gigantic black hole at the center of almost every massive galaxy. Whenever those black holes get together, they form this pair that send out these waves of gravity that we need different types of detectors to measure. And this is not the kind of wave that is peak to peak a few seconds. This is the kind of wave that has peak to peak times of years to decades. So this requires patience. And it's something that I've been doing for the last 10 years. But really, it's not just one wave that we're looking for. It's not just one single pair of black holes. Really, we're getting waves of gravity from almost every pair of black holes throughout the universe. There are hundreds of billions of galaxies in the universe. All of these pairs of galaxies are potentially interacting, colliding. And as they do so, they're sending out ripples of gravitational waves that creates an ocean of gravitational waves, and the Earth is bobbing at the center of this ocean of gravitational waves. We have to be very careful how we go about measuring it, but really we're listening to an entire symphony of gravitational waves. It's just very, very low frequency, so this would be the brass section of gravitational waves. So we've got all of these pairs of black holes all radiating, sending out these ripples of gravitational waves towards us from the depths of the universe. And really, in order to get a measurement of those kinds of gravitational waves, we need to have something that is like an astronomical clock. A clock out there in the universe that's going to help us detect whether gravitational waves are causing changes in astronomical distances. So we're almost looking for ocean buoys in the universe that can act as standard reference points in the universe. Fortunately, we have a great type of detector that does that, and those are called pulsars. Pulsars are essentially dead stars. They're what happens just before a star will collapse into a black hole. They're the most dense form of matter that's possible, and a spoonful of neutron star material would weigh as much as a mountain. Okay, so these are ultra-dense stars. And these pulsars are basically neutron stars that send out beams of radiation and spin around. So you can almost think about these like cosmic lighthouses. Every time the beam spins around, it will send a pulse towards us, and we measure those pulses. Okay, so it's like almost like a metronome as well. And we time those incredibly well. A little bit more about these pulsars. Like I said, they're neutron stars. They're more massive than the sun, but they're the size of a city. And they're spinning as fast as a kitchen blender. So if that doesn't excite your imagination, I don't know why. That's an incredibly extreme system. Another great thing is that they were first discovered right here in Cambridge by Jocelyn Bell in 1967. Originally, she was using a chart, like a chart recorder. And this is one of the first observations of pulsars in 1967 that she called a little bit of scruff in her measurements. But her, with her advisor and collaborators, persisted with this measurement and discovered the first 3 pulsars, which is extraordinary. And I think it's worth pointing out, given that it's International Women in Science Week. All right, so here's Cambridge, just for reference. Here is a neutron star in the middle of Cambridge. So this is a very, very dense object. This is something that's as massive as the sun, squeezed into something just a little bit greater than Cambridge. Now, what do gravitational waves do to the timing of these pulsars? So every time this pulsar spins around, it sends a nice pulse towards us, and we can measure that, time that incredibly well. If a gravitational wave comes in, it's going to stretch and squeeze the space between the Earth and the pulsar, and it will cause those pulses to arrive a little bit earlier or a little bit later than expected. So it causes these offsets in the timing properties of these pulsars. And we can measure that we can use that to find these gravitational waves. So instead of just doing this with one pulsar, we build a network out of the ones that we can see in the Milky Way galaxy. So instead of thinking about that nice L-shaped thing that's a few kilometers across that measures gravitational waves, and it's called LIGO, this is the nanograv detector. So this is something that spans our little neighborhood of the Milky Way. And it's made out of almost 70 pulsars that we've timed. There's the Earth at the center there. And as these waves wash through the network of pulsars, they're stretching space and time in a very distinctive way and allow us to pick up echoes of gravitational waves from all over the universe, from the most massive black holes that can exist. We do use radio telescopes in order to make these observations. So some of these might be familiar to some of you, especially if you're a movie fan and have seen Contact or the James Bond movie GoldenEye. Unfortunately, Arecibo collapsed in 2020, so it's no longer operational, but certainly VLA was in Contact as well. And the Green Bank telescope, well, that's just a very cool telescope. I don't know if it's been in any movies. This is NanoGrav, which is the North American Nanohertz Observatory for Gravitational Waves. But when I was here, I first started out in the European Pulsar Timing Array. And really, there's an international network of collaborations that are doing this using telescopes all over the world, from Europe to Australia, China, India, South Africa, and in North America as well. So it's a really great international collaboration. I think I'll skip over just this image of what's happening here, but we had our own little breakthrough in 2023 at the end of June, where we looked at the timing properties of all of these pulsars. We then looked at the overlap in the timing similarities, and we found that with gravitational waves, we should expect kind of a commonality in the timing properties between separated pulsars, vastly separated across the Milky Way. And that only happens if you've got gravitational waves washing through the network and jiggling the Earth as it looks at all of these pulsars. So you get this nice pattern here that's very distinctive. And then this is what we measured at the end of June last year. So to celebrate that, we had lots of media pick us up. These are front pages of the Washington Post, and then we had the New York Times as well. I was very excited that we made the front page of the Washington Post. I had a lot of coffee that morning, so that's my explanation for it. And then if you're a fan of Steve Martin, the comedian and actor, he also had some intuition that this was coming somehow and tweeted about us, this discovery of the low-frequency gravitational wave universe. So, to tell you a bit more about my journey and really to finish us off, when we first started looking at this very long data set, 15 years of observations, this was in spring of 2020. I think we all knew what we were doing in spring of 2020. I started first doing analyses while I was on my sofa in spring of 2020. This is my research assistant. And then fast forward to when we actually made the announcement. We did it at the National Science Foundation in Washington, D.C. We were joined by Kip Thorne, who's the Nobel laureate in physics in 2017. And in a very historic moment as well, we were joined online by Jocelyn Bell, who discovered pulsars in the first place. So it was a nice way to round out this part of the story, especially since we've been doing this for so long, and we have lots of people that have dedicated big portions of their career to make this possible. It seems like a ridiculous concept that we can make the galaxy do this for us, but it's something that's been done, and we look forward to the future, especially as we work with more of our international partners as well. This is a big global effort, and I'll be excited to come back in a few years and tell you more about what we might have found in the low-frequency gravitational wave universe. Thank you very much.
Excitement just bubbling up. Do we have any questions? Questions for our speaker? Questions from young people are allowed, it's okay?
Yes, please, encouraged.
Yeah.
Yeah.
What happens if there was a star, and on its right there was a black hole, and on its left there was a black hole? What would happen?
That's a very good question. So the question was, for anyone that didn't hear it, what would happen if there was a star, and then on one side of it there's a black hole, and the other side of it there's a black hole? If the star was very close to both of those black holes, you would just see it get sort of torn apart Imagine taking a piece of mozzarella cheese and just tearing it apart. That's what would happen to that star until eventually it just all of that stuff that the star was made of would get sucked into those black holes.
Yes, please.
So, when you were detecting these gravitational waves, how were you able to tell where they actually originate or came?
That is a great question. So the question was, how do we tell where the gravitational waves come from, where they originate from? So in this signal, really we're looking for an all-sky background of gravitational waves. It's kind of like the cosmic microwave background, except it's the cosmic nanohertz gravitational wave background. But we think that this background is ultimately made up of individual systems, pairs of black holes that are radiating gravitational waves. And if we keep observing for longer, we think only another few years, we should start to see the really bright or really loud gravitational wave systems sort of come into focus, resolve out of that background. And being able to actually find where it comes from in gravitational waves is very challenging. It's a big patch of the sky that we have to search on. But as we observe longer, we can hone in on that region of the sky and then look at possible galaxies in there that might be hosts. So, yeah, it's a good question.
Yes, please.
If there are black holes that take in stuff with good gravity, shouldn't there be another thing like an anti-black hole that would like blow through the web?
That's a great question, and that's a budding quantum, gravitational theorist there, I think. So there are indeed theoretical objects called white holes that instead of sucking in things will blow out things. Some people have even, hypothesized that the Big Bang was sort of like a white hole because it spewed out lots and lots of material instead of sucking things in. So it's a good idea in theory. They should exist. We just haven't seen any yet that we think.
And yeah, front.
What's the black hole made of?
Again, a great question. So the answer is nothing. It's not made of anything. It's really just an area of pure gravity. So it's something that is completely dark and it's not made of stuff. There's no material there. We can't, knock on it and say that there's something there. It's just an area of space that's it's like a pinprick in the fabric of space. And if anything goes near it, it will fall into it, and we don't know what happens to it then. It's not as scary as it sounds. It's if you replace the sun by a black hole of the same mass, all of the planets would still orbit around that black hole. It wouldn't suck in the material any more strongly than the sun. It's just that obviously we rely on the sun for other things like heat and light. So we'd know about it after about 8 minutes, whenever we didn't get any light from the sun anymore.
Yeah, please.
Yes, so you explained gravitational waves. When they hit your sensors, you can detect them. But what if there are waves where the amplitude is much longer? So that, let's say we're on the peak of the wave for hundreds or thousands of years.
Yeah, we just wouldn't be sensitive to those. Every type of detector, whether it's in a detector in a lab or it's a detector like we've got, has a certain, kind of region of sensitivity. And if you go outside that, you're out of luck, unfortunately. So there should be lots more gravitational waves at lower frequencies. If you go to ultra low frequencies, then you can start to look for those gravitational waves in patterns in the cosmic microwave background. People are still trying to do that because those types of gravitational waves should be very exciting. Those might actually be relics from the very start of the universe. So people are still looking for those.
Okay, let's do 2 more questions, sort of at the front, and then maybe you in the middle. Are you happy maybe to stay around?
Absolutely,
for
yeah.
any more questions? So at the front.
If a tiny black hole with so less gravity comes across like a really big black hole with lots of gravity, will the small black hole get sucked into the big black hole?
Great question. So yeah, the question was, if there's a small black hole near a bigger black hole, would the smaller one get sucked in? Yes, it would. It would, again, it wouldn't look like something colliding. It would just look like a tiny little bead of water that merges into a big puddle and it forms a bigger black hole. So it doesn't look as exciting or catastrophic as you might want it to look, but it does happen in the universe. And there's a big detector that should be launched in the middle of the next decade, so in about 10 years, when you'll be at university, so it's a good thing to study. And it should find those types of gravitational waves. So keep asking those questions.
Okay, and let's do the last question from the beamer there. in the front.
How many people have died from the black hole?
How many people have died from a black hole? None that we know of. Maybe some indirectly, just through shock of seeing the signal or thinking about them. But no, they're not. It's not something to be afraid of. They're no more dangerous than any other type of star. Like I said, if you replaced the sun with a black hole, everything would still move around the black hole just as things move around the sun.
Excellent. Okay, so I've just got a text from our observers. It is clear, they are set up, they are ready for our stargazing. I'm going to lead you outside. Just a note before we go out. That what you're going to be presented with is you're going to be on the lawn. There's going to be a bit of a stargazing show on the screens. There will be some students in a telescope off behind the trees with